Okay, so now we've made it through discrete random variables. We want to talk more about continuous random variables now. So again, we're going to introduce some general notions. We're going to have a probability distribution just like for discrete random variables. Except now instead of having a probability mass function, we're going to have a probability density function. And this is going to be f of sub capital X. And it's going to map the random variables, which are real numbers, into the half-closed interval 0, infinity. Okay, so the PDFs are non-negative values. And they only have to satisfy one condition, which is that their integral from minus infinity to infinity is 1. Okay? And again, we're going to define the support of the random variable as all the real numbers for which the density is greater than 0. Now we say the continuous random variables have a sample space that is an interval, and so the events are going to be intervals also. And so what's really important to understand is that given some interval I, what's meaningful to ask is what is the probability that a randomly chosen value of the random variable is in the interval I. Okay, that's what it's meaningful to ask probabilities about. And the way we get that probability that the random variable is in some interval is we integrate the PDF over that interval. Okay? It's important to understand that this fact implies that the probability that x has a specific value is 0. Because what happens when we integrate a function over a point? We get 0, right? Because integrals are areas. Okay? So the PDF is not the probability that a value has a certain, the random variable has a certain value. Okay, that's 0. But the PDF, when we integrate it, gives us probabilities. Now, just like we had a CDF for the discrete, we're going to have a CDF for the continuous random variables, and it's defined the same way. A couple of important properties of the CDF is that if we go with the definition, we realize that this condition means that capital X is in an interval. And when we go ahead and we integrate the PDF over that interval, we notice that there's a relationship between the CDF and the PDF. The PDF is the derivative of the CDF by the fundamental theorem of calculus. Remember that? A couple of things that you can show is you can show that the CDF is monotonic increasing. It's a function that goes from 0 to 1. The limit as x goes to negative infinity of the CDF is 0. Okay? And the other asymptotic behavior we can show is that as x goes to positive infinity, the CDF converges to 1. These things are a little harder to prove. You can prove them, but I won't ask you to. But you should be able to prove that the CDF is monotonic. That's pretty straightforward. Okay. Now, how do we get expected values? Well, it's really the same as the discrete random variable. Notice for the discrete, we took the values of the function and we multiplied it by the weights from the PMF and we summed over all the discrete values. Well, for continuous, instead of taking a sum, we're just going to change that to an integral. So this gives us a definition of the expected value of a function of a continuous random variable. Important to understand that all of the properties of the expectation operator that held for the discrete hold for the continuous. It's still linear, things factor out, it distributes over sums, okay? And the mean and the variance for the continuous random variable are really defined analogously. If we simply replace the sum by an integral, the mean of the random variable, which we, for a continuous random variable, we usually call mu, is just this integral of x times the PDF integrated from minus infinity to infinity. It's really the same as this. And the variance again is the expected squared deviation of the random variables from the mean. And we can show in the same way that the variance, which is called sigma squared because it's the square of the standard deviation, is the expectation of x squared minus the square of the expectation of x. So all of these definitions kind of go over the same way, just substituting integral in for some. Now there are two things that are really important. We often want to transform a PDF because instead of the variable we have some function of a variable. And there's two different ways we can do this. So I want to show you how. The first is where we directly transform the PDF. So if x is a random variable, its PDF is f sub capital X. And we now have a function of the random variable, which is a new random variable, where this function g is 1 to 1. That's important. Then the PDF for y is given as the PDF of x evaluated at g inverse y. Excuse me 1 second. Okay, why is that? Because, well, what is x? X is g inverse of y, right? But I have to multiply by the derivative of the g inverse of y with respect to y and take the absolute value. Okay? And there's a reason behind this derivation. I won't go into it, but it's not hard to see. It's kind of the chain rule. Okay, f of x is the derivative of the CDF with respect to x. So it's df dx, and this is dx dy. So it's just the chain rule. I want to show you how this works with a very important example. Okay, we're going to suppose that x is a random variable and it has this PDF. And we're going to see later on this is the PDF for a normal random variable. And I want to look at a new random variable. It's a function of the old random variable. It's going to be x minus mu divided by, and this should be sigma. I'm sorry for that. Let me change that real quick. And you probably recognize this. This is just the standard normal random variable. Okay? So I want to figure out now, what is the PDF of z? Well, it's not difficult to show that g inverse of z is sigma z plus mu. Okay? And therefore, when we take the derivative, we just get sigma. We don't even need the absolute value sign because sigma is always positive. And so I'm going to plug it into this formula. Where x used to be, I'm going to put g inverse of z. And you can see what's going to happen. The mu's are going to cancel, the sigma squareds are going to cancel, and I get this nice form. And the sigma down here, of course, cancels with the sigma up here, and I get this. And you probably recognize that is the PDF for the standard normal random variable, but this is how we get it from this. Okay? Now sometimes there's a problem. So sometimes the function g is not 1 to 1. The question is, what do you do then? Well, we have a second way called a probability integral transformation. And really what it is it's a variable transformation where we're working off of the CDF as opposed to the PDF. So let me show you kind of an example because the method's a little hard to explain. The idea is that we start off with the random variable. We know it's PDF. We know it's CDF with respect to x. And now we have some new random variable. And what we're going to do is we're going to express the CDF in y in terms of the CDF in x. And then we're going to take the derivative with respect to y and get our final answer. And let me show you because it's a little hard to explain. I know that. So here's an example where x is a random variable and its PDF is going to be 1/2 on the interval -1 to 1. Okay? So this is x. It's a uniform random variable on the interval -1 to 1. And now I want y to be equal to x squared. And I want to know what is the PDF of y. Okay, so what I'm going to do is I'm going to start with a CDF for y, and I'm going to convert it, I'm going to express it as a CDF involving x. So I start off f of y, which is the probability that capital Y is less than or equal to y. This comes from the definition. And now I'm going to substitute what y is in terms of x. Capital Y is equal to capital X squared. Okay? And now I'm going to convert this to a CDF in terms of the random variable capital X. I'm going to say, okay, if x squared is less than or equal to y, then x is between minus the square root of y and positive square root of y. And you can show that this is equal to the difference of these two probabilities. Okay? And so now this is equal to the CDF of square root of y minus the CDF of minus the square root of y. And I can simply take the derivative with respect to y. And that ends up giving me my PDF in terms of y. And actually this last one, I'm sorry, I have to be careful here. This is actually 1 minus the CDF evaluated at minus the square root of y. And I think for a homework problem, I'm going to let you sketch out these details. I think it's kind of worthwhile to do that. Okay, next we're going to look at some actual continuous distributions, ones that you're probably familiar with, and learn a little more about them.